Hello and welcome to the fourth seminar of Public Health 1, which is about statistics. In this seminar, we learn the basic concepts and principles of medical statistics. And before we go to this part, I would like to share with you the answer of this question. Why statistics is important for medical students? As a future medical professional, you will frequently encounter clinical studies, like in form of research articles abstracts and conference. Understanding statistics enables you to critically assess these materials. You will need to evaluate the methodology, for example, you will need to scrutinize the results or interpret them and consider applicability of these findings. So if you are statistically literate, this will help you to make the judgments with good sense of understanding. Then, once you have this skill, or once you are able to interpret medical literature independently, you will have greater opportunity or skill also to make clinical decisions. Every interaction with patient involves a series of decisions. This ranges from diagnosing symptoms to selecting tests or treatments, and statistical principles that underpin these choices, for example, when we talked about sensitivity and specificity in the second week of diagnostic test, these can influence your decision to employ it. So based on learning the and also understanding what sensitivity and specificity of each test could be, you will decide which test you will use in these particular cases. And once you make these decisions as we aim to make it should be evidence-based, and learning the numbers and understanding what these numbers really mean will definitely help you to make your decisions sound or based on evidence. Also think about biological variability, because medicine deals with biological systems that are inherently variable. For example, not everyone exposed to pathogen will react in the same way. Responses can range from asymptomatic to severe illness. Statistical methods can help you make sense of this variability and draw valid conclusions. Again, we are not dealing with rigid systems. Biological systems are so flexible, and understanding the variability in human bodies will definitely help you to understand the differences in outcomes you will see in your patients. And finally, being able to interpret medical literature and read it like frequently and rapidly, this will keep you up to date with new medical technologies and medical advancements in whatever clinical specialty you will pick up in your future. So all these reasons are just a summary of why medical students and future medical doctors need to be statistically literate. According to the World Federation of Medical Education, there are certain requirements for statistical knowledge and statistical capacity, either in undergraduate medical education or even in postgraduate courses and residency programs or specialty programs. The same in the UK and US and other national accreditation guidelines for medical education. It is important for medical students, as you probably understand now, to be statistically literate. So today's seminar has some sections that are organized in a logical manner to help you understand all foundational concepts in medical statistics. We start with variables that are characteristics that could describe the patient's outcomes and how we can describe them using descriptive statistics methods, inferential statistics, which try to answer the question of if something is associated with something else. Also, we will learn the concepts of prognosis and survival, validity and reliability, and finally bias and error. So let's start with variables. Variable is any characteristic or attribute that can be measured. Think about any human, not necessarily patients, but any average human. These humans will usually have characteristics that we can measure. For example, age. We can tell the age of any human using number of years or number of months. The same for gender. It's kind of groups or categories that we can easily report. Weight, height, these are also numbers. Race, this can also be groups. Blood pressure, respiratory rate, bone density, these are all potential numbers. So we can measure them, we can report them, and this is easy. But think about morality, maybe kindness, maybe wisdom, compassion, integrity, love, sense of humor, and faith. These are all characteristics that can yet also be used to describe humans. However, we have no method to measure them. That's why these are called non-tangible characteristics, because we cannot measure them. However, those that we can measure are called variables. So in a nutshell, any characteristic that can be measured is a variable. It can be measured using numbers or using groups, or we can classify it into groups. It doesn't matter. Once we can measure it, once we can classify it, this is a variable. But if we cannot classify it, if we cannot measure it, this is a non-tangible characteristic. There are two main types of variables: the variables that can be described using words only, and the variables that can be described using numbers. So the qualitative variables cannot be counted. That's why we cannot use numbers to describe them. However, the quantitative variables are in fact numerical variables that can be easily described with numbers. So the first subgroup of qualitative variables are the qualitative variables that have no difference between the groups that are described, like what we call categorical variable. The best example is gender or sex. We have males and females, and there is no difference between males and females. They are supposedly equal, and they are actually equal. That's why we cannot see any order. We cannot see any like inherent hierarchy in these groups, and that's why they are all equal, and these are categorical variables. On the other hand, there are other variables that can yet also be described using words. However, there is some sort of hierarchy in between or between them. This is, for example, the body mass index groups. So we have underweight, we have normal weight, we have overweight, we have obese class 1, obese class 2, obese class 3. These are all different groups of individuals, and using the words to describe their body mass index, yet it's qualitative, we cannot see numbers yet. However, this is a hierarchical order or ordinal variable. So qualitative categorical variables describe groups that are equal. Qualitative ordinal variable describe groups that have some sort of hierarchy between them. Then, when we look at numerical variables, we have two main groups: interval variables, and we will describe them very soon as those variables that have no actual zero or no physical zero, which means that they have 0 point, but this zero does not represent the case or the phase of no existence, yet the variable can still exist even though the value is 0. And we have ratio quantitative variables, and those are the variables that have physical 0 or actual 0. So when the body height is 0, it means that this body is not existent. There is no height at all. The same also for Kelvin temperature. We cannot reach the 0 Kelvin. That's why it is a quantitative ratio variable, because 0 here means the phase of no existence that is impossible to be achieved. Okay, so let's see in more detail these types of variables. Let's start with categorical. It has another terminology or other synonym, which is nominal, and this is a variable that can be divided into distinct categories without any inherent order, as I said. On the other hand, we have ordinal variables that have an intrinsic hierarchical structure, while the intervals between adjacent categories lack a quantifiable uniform scale. We cannot see the space between the groups or the levels in the ordinal variable. However, we know that the higher strata are supposedly more prominent than the lower strata, yet we cannot see the distance between them. So in this table, you can see some examples of categorical and ordinal variable. Gender, as I said, is male, female, no difference. Blood type can be A, B, O, or AB, no difference between them, like there is no better blood types than others. They are all the same. Disease status, we have someone who is healthy, someone who is infected. Vaccination status, we have someone who is unvaccinated, someone who is vaccinated. These are all binary variables or dichotomous variables. So these dichotomous variables or binary variables are not hierarchical. Okay. Then we have ordinal variables. For example, cancer stages. We have stage 1, 2, 3, and 4. We know that the patients who are in stage 1 are supposedly healthier than the patients who are in stage 3 or stage 4. Yes, we cannot see the difference. We have no numerical tool to tell how much the stage 1 is better than stage 2 or stage 3, yet we know that stage 1 is early stage of the disease. That's why it's supposedly better in terms of prognostic and outcomes. The pain scale, any visual analog scale like this one will describe different levels of pain, ranging from no pain to like extreme pain. The more you go upward, the worse the pain could be, but yet we cannot see the exact distance between the stages, and that's why this is still an ordinal variable, but we know that like the more you go upward, the worse the pain could be. The Glasgow Coma scale, even though it uses numbers, but this number does not describe like actual differences. Because the scale is a composite scale having three domains: the eye-opening response, the verbal response, and motor response, and it ranges from 3 to 15. 3 means a human who could unfortunately dying or in a severe coma, and 15 means a human who's like perfectly responsive. And as you can see, the scale or the number can be based on different rates from the three subconstructs, and that's why it's not like quantifiable yet. At the education level, we have high school, we have bachelor or master degree, we have PhD level. All these educational levels are ordinal, because we know that PhD is more advanced than high school, for example, but yet there is no way to visualize or measure the difference between these levels. Okay, so this was qualitative variables that we describe using words only. We have no numbers to describe the difference between these groups, and categorical variables have no difference between the groups. Ordinal variables have some sort of order or some sort of hierarchy between the groups. Then we have the interval variable, which are the numerical variables with a consistent scale and no true 0 point, which means that there is no true or physical 0. And these interval variables are useful when we try to have an idea or a sense of differences. However, ratio variables are more accurate if you would like to think about them like this, because they have true 0 and they can show the ratios between the levels in the variable. So let's see some examples. In interval variables, we have the IQ score, the intelligence quotient. And in intelligence quotient, you cannot say that if someone has 0 IQ, which is not common, but let's assume that there is some animal or some creature that has 0 IQ, you cannot say that they have no intelligence. Yes, they still have intelligence. You can describe them as super stupid or super dumb, but yes, they have some sort of intelligence. Celsius temperature, when we have Celsius or even Fahrenheit temperature, which is 0, this doesn't mean that there is no temperature. For example, if you have Celsius temperature 0, it means that the water is freezing, for example. And this pretty much means that you can even go below 0 and you can have -1, -2, and etc. That's why 0 here does not imply no temperature. It means that the temperature is very low. The same for the pH level, because when you have a 0 pH of any solution or any material, it means that this material is extremely acidic. This doesn't mean that it doesn't have pH, it means that the type of the solution is extremely acidic. Also for calendar years, if you think about the Julian calendar that we use for today, the year 0 doesn't mean that there was no year at this time. It means that this was the year of Christ's birth. Before it, it was before Christ. After it is after Christ, or like today in like 2023. So 0 doesn't mean no year. It means a year that this calendar is divided into two equal parts. So all these variables, when they have 0 value, it doesn't mean that the variable disappeared. It means that these variable is just, consistent on a scale, and it can help us to see the differences between the levels. On the other hand, ratio variables can describe very precisely the distances between the levels. For example, age, you have any number from 0 to infinity, and if you, for example, look at the difference between the 10 years to 20 years, which is 10 years precisely, it is the same exact distance when you look at the age 30 to 40. it's also 10 years, and this 10 years is equal to this 10 years. So age is a ratio variable. Also, because when you say that this human or this disease lasted for 0 days or 0 years, it means that it did not exist at all. Okay, so if a disease lasted for 0 days, it means that this disease did not happen. If a human has 0 age, 0 days, or 0 weeks, it means that this human is not existing or didn't live at all. Okay, so this is age. Also for the body mass index, actually body mass index is a ratio. It is a ratio between weight and height. And if someone has 0 BMI, it means that this human is not existing at all. The same for income. If someone has $0 as an income or €0 as an income or whatever other currency, it means that they have no income. And the speed is also a ratio because it's the ratio between distance and time. And if a car moves with 0 km/h speed, it means that this car does not move at all. Okay, so speed in this case will disappear entirely. Okay, so this was the interval and ratio variables. Also, numerical variables can be described using discrete or continuous numbers. So discrete numbers are the numerical variables that have distinct values and cannot be subdivided. So this is 0, 1, 2, 3, and etc. However, continuous variables, those are the numerical variables that can be organized on a continuum of values or can take an infinite number of values within a given range. So it can be 0, 2, 3.2, 3.5, 3.7, and etc. Example for discrete variables is the number of hospital admissions. So we can tell today we had 50 admitted cases. Yesterday we had 45, the day before we had 60, and etc. So you cannot have 30.7 or 30.8 admissions because it's impossible. The same for number of lost teeth. If you would like to count the number of lost teeth in any human, this will definitely be a true number or a discrete variable. The same for priority in obstetrics, like how many babies a fertile woman can give or already give. This is number of humans, number of babies. That's why this is, or number of pregnancies to be precise, this is definitely a discrete number. Number of medications prescribed, the same. However, on the other hand, when we look at blood pressure, this can be any value, like it can be 120.5, 121.7, and etc. So this is not necessarily a discrete number. It can be anything in between. The blood glucose level. The blood glucose level as well, it can be 100.9, 100.8, 100.7. So this is a continuum of values. The body temperature, it's supposedly 37.2, 37.3, yet these are all continuous variables. And finally, the height, which can also be a continuous variable. So both discrete and continuous variables are subtypes of numerical variables, and both the interval and ratio variables can be described with discrete or continuous numbers. Then we have other dichotomy to describe variables, which is independent or predictor variables and dependent or outcome variables. Independent variables are the variables that are manipulated or categorized to observe their effect on dependent variables. So those are the characteristics that will influence the others or will lead to the others. However, the outcome variables, those are the results of the independent variables. Think about smoking and cardiovascular disease. Smoking can be a predictor. It can lead or it can influence the cardiovascular health and it may lead to disease. On the other hand, the cardiovascular disease itself is the outcome of smoking, which was the predictor or the independent variable. Okay, so some examples for independent variables could be dosage of medication. So if you think about a clinical trial where different groups received different dosages of the medicine to be tested, this is, I mean, the different dosages, this is the independent or the predictor variable. Also, exercise frequency. If you look at a cohort study with different active or physically active groups, the exercise frequency is the predictor for whatever outcomes that we will see later on in terms of fitness or their cardiovascular or respiratory or other health areas. Then type of surgical procedure. If you are in clinical trial and comparing different surgeries to see the outcomes of the patients later on, this is definitely the predictor or the independent variable. The smoking status, if you compare smokers to non-smokers, smoking status itself in this case will be the independent variable or the predictor. On the other hand, the outcome or the dependent variable are the results or the things that will happen based on manipulation of the independent variable. So, for example, the tumor size or the stage of the cancer, the blood sugar level, this is a result from, let's say, smoking or physical sedentary, the mortality rates from some disease or some problem, the quality of life scores. These are all dependent variables or outcomes that will be based on the differences in the independent variables. Then let's think about this example, age. How can we describe age? We have probably several methods or several ways. We can describe age as 5, 11, 24, 57, 86 years old, and we can also describe it as 11 years, 4 months, 15 days, and we can say it as 11.37 years. And we can also describe age as young age, middle age, or old age, right? So age is a concept that can be described using several formats. If we gonna use the first format, this is a quantitative because we use numbers. This is ratio because we use numbers that have true zero. We say that if someone has 0 age or 0 years, it means that they didn't live at all. And this is discrete because the numbers here are true numbers. It's 5, 11, 24, 57. Okay. In the second method, we have also quantitative ratio, but it's continuous because the values here can be anything between 1 to 2 or 2 to 3, like it can be 11.37 as you can see. So these fractions or these small parts, if they are used, this means that the variable that we see here or the numerical variable that we see here is a continuous variable. And if we just use words, this will be qualitative and it's also ordinal. Okay, so it's an ordinal qualitative variable because we know that the people who are described as old, they usually have more years or more age than those who are middle age or young age. And we commonly refer to this as the age group. So age group is a qualitative ordinal variable. If we use just numbers that are true numbers, this will be discrete. If we use numbers that are continuous numbers, this will be a continuous ratio variable. Okay, so as you can see, the same concept or the same characteristic can be described using different variables based on what we would like to present in our data and how much information we collected from the field or from the patients. And it's up to the researcher to choose the best format. Okay, now let's move to the second part of this seminar, which is about descriptive statistics. In a nutshell, we have this question, how we can describe variables, how we summarize them. If we use or if we have qualitative variables, then we're gonna rely on frequency and percentage. If you look here in this table, we have gender, which is definitely a qualitative variable, which is categorical variable to be specific. We have female, male, and prefer not to say. And as you can see, we described it using frequency, which is the number of individuals in each of these groups, and also percentage to the total population or the total sample. Okay, so if you have qualitative variable, you can fairly describe it using numbers or frequency and percentage, which is, as you can see it here. Also, if you have quantitative variables, you have two concepts to be used, either central tendency or dispersion. And very soon we will learn what are the measures of central tendency, that are mean, median, mode, and the measures of dispersion, which are variance, standard deviation, range, and percentile. So let's think about quantitative variables. Quantitative variables are often displayed using frequency distribution figures. This is, for example, a frequency distribution figure. In this figure, if you look at the x-axis or the horizontal line, this describes the fasting blood glucose level, which is, as you know, is a continuous variable or quantitative variable. Also, the number of cases, this is another quantitative variable, and it's described by frequency, and this is on the y-axis or the vertical line. Okay, so if you have the quantitative variable that you would like to describe here, which is the fasting plasma glucose, you're gonna use the frequency distribution figure. And this figure describes the count or the proportion. Here we use the count, which is frequency, or proportion sometimes if we use the percentages of the individuals in each specified group. So, for example, if you look at the fasting plasma glucose level of 120, this is one group. 130, this is another group. 140, this is another group. So each line or like each blue bar here represents the number of cases that have, for example, 120 mg for each DL fasting plasma glucose. And in order to describe these figures easily, or like write them on tables or in like textual form instead of just looking at the graphs, we use two characteristics of these figures. The first characteristic is that most of these figures have a central area that gather most of the values, and this is called the central tendency area. And also, the other values that spread around this area are called dispersion, and there are measures for both central tendency and dispersion. Let's start with central tendency. Central tendency refers to the statistical measures that identify a single value as representative of the entire population or the entire distribution, serving as a central point around which the data values cluster. We have mean, median, mode that describe central tendency. And before we learn what are each of them and the difference between them, let's look at this example. In this example, we have a list of 20 children and the age of each of them. So the first child has 10 years old, the second one has 7 years old, the third one has 11 years old, and you can read the rest. So if you would like to learn what is the mean of this sample, mean, by the way, is the easiest to be calculated if you would like to know, because this is the arithmetic average of the values. So this pretty much means this is the sum of all ages of all the students or all the children divided by the number of the students or the children, and this was 20 children if you remember. And in this case, the sum was 171 divided by 20, and this was 8.55 years old. So this is the mean. The mean is amazing because it's sensitive to all data points widely used, so it does not ignore any extreme values or outliers. However, it can also be affected by the outliers, which is the drawback of mean. At the same time, we can get median. And in order to get median, you need to organize the values in an ascending hierarchy. So instead of 10, 7, 11, and etc., you need to organize them ascending from the lowest value, which was appearing here as 5. Then we have another case which had 5 also years old. Those are the cases number 12 and the case number 15. Both of them had the age 5. Then we have two cases that had the age 6, which are the case number 6 and the the case number 18. Both of them had 6 years old, and you can see how we organized in an ascending order all the ages of the cases. And you have to look at the midpoint, the case that divides all these values into two equal halves, which was between 8 and 9, because this was an even number. And if we have even number, we will look at the two middle values, which was 8 and 9, and we get the sum of them and divided by 2, and this will make the median as 8.5. So median usually is close to mean, but it's not necessarily the same value, and sometimes the distance between mean and median mean that the distribution of the sample is not normal, and this is what we will learn very soon. So it's very important to keep an eye on mean and median and see how much similar or how much far they are from each other. Then we have the mode, and mode is very simple. You just have to organize the values, as you can see, and look at the most repeated value. And in this case, the most repeated value was 11. That's why this was the mode. In this slide, we have made a summarization for these three values: the mean, the median, the mode. And as you can see, the mean and median was pretty similar to each other. I mean, they were pretty close. However, the mode was far away because this was the highest or the most repeated value. It doesn't necessarily to be the highest one, it can be the lowest one even, it doesn't matter, but this was the most repeated one, and it was 11. Okay, so as you can see, mean and median are close. Mode is the most repeated one. Let's see why mean and median should be continuously measured and compared. First, in this scenario, we have a city that has a normally distributed household income. So as you can see, the income of the individuals in the city are organized in a kind of a pyramidal shape or belly like shape, where the area when most of these values are surrounded or gathered. This is a center tendency area, and the mean was 50,500 and the median was 50,000. This is perfect because the mean and median has no much difference. However, in another case, and imagine the city is a city of some billionaires, like the most wealthy Forbes men or human, and if you have this small group who earn a lot compared to anyone else, in this case, the household income will not be normally distributed. It will be definitely skewed toward the higher values. And if you compare the median and mean in this case, it will be really surprising because the median is 50,000, however, the mean is 300,000. And when you look at the location of mean, which is this red line, you cannot see any middle area. You cannot see any value even. This is almost no area or nowhere. So the problem with the data sets that have outliers is that they can easily screw the location of the mean, and the mean will not representative or indicative for any like central tendency area. That's why in this case, if you have a non-normally distributed data, you should use median, not mean. Okay, now let's look at dispersion. And as I say, dispersion describes the extent to which the values in a dataset deviate from the central tendency. So this is the areas or the data that are around the central tendency area. And it has some metrics like variance, standard deviation, range, percentile, like decile and quartile. We will learn each of them right now. So getting back to the same examples that we had earlier, which are the 20 children that have different ages. If you would like to get the variance is simply based on deviation. But what is deviation? Deviation is the difference between each value in the dataset, I mean each age of these 20 children, minus the mean of the sample, which was 8.55. And once you get the deviation for each case recorded, then you need to get the square of this deviation. And you get the sum of all these square deviations and divided by the number of cases, and this will be the variance. So for example, the first case had 10 years old. If you remember from previous slides, we had said that mean or the average was 8.55. So 10 minus 8.55 squared plus 7, which is the second case, minus 8.55 and also squared plus 11 minus 8.55 all squared plus the third case and sorry, the fourth case, and etc. And all should be at the end divided by 20. For example, 10 minus 8.55 squared is 1.45, and you can do the rest for the 20 cases. And finally, the variance in this case will be 4.475. All right, so this is the variance. And again, variance is the average of the squared differences from the mean. It's good because it takes an account all data points. However, it's not directly interpretable. But it's important, as I said, because we will use it for the next step, which is standard deviation. And a standard deviation is a square root of the variance. So it's like directly interpretable, and unfortunately it can be somehow affected by the outliers. So standard deviation is a square root of variance, and if you remember, variance was 4.0 and this was 2.1, sorry, 2.012. Okay, so this was the standard deviation. Range is when you look at the values of all the children and try to reorganize them in an ascending order from the lowest value to the largest value, and then pick the minimum and the maximum value, get the difference between them, which was 6. So range is 6 because the lowest value was 5 and the maximum value was 11. Then if you'd like to look at decile or quartile or any other percentile, you need to also organize the data from the lowest to the highest, again in ascending order. And when you would like to look at the top decile, which is the top 10% of this population, then you should look at the highest two children, and their age was starting from 11. If you would like to look at the second decile, then you should look at the top 20% of them, and look at the first case of this 20%, and it had also the age of 11. If you look at the ninth decile, which is almost the highest or the top 90%, you should look at 90% of the cases, and they start from the age of 6. The top quartile means this is the top 25%, and in this case this was the highest 5 cases, and they started from the age of 5. On the other hand, the third quartile is the top 75%, and this was the highest 15 cases, and they start from the age of 7 years old. Okay, so percentile, in order to be measured either for deciles or quartiles, you need to organize the data from the lowest to the highest value and then see what is required. All right, so as you can see, range and standard deviation are a little bit different. Range extends from the lowest value to the highest value, as we learned earlier. Standard deviation is focused on the values that are around the mean. Okay, so it describes how much the values, the central tendency values around the mean looks like, I mean, to which direction. And usually speaking, you can get an limited number or infinite number of standard deviations. One standard deviation describes usually 2/3 of the values in the population, and this in case of perfect or normal distribution. If you don't have even normal distribution or somehow normal distribution, one standard deviation will also include more than 2/3 of the cases. And if you look here in this graph, you will understand why it is important to keep an eye on range and standard deviation. And the first city that we say that has normal distribution, the mean was 50,500, the median was 50,000, which is amazing, and the standard deviation ranged from 43,000 to 57,000, which is okay. And as you can see, the standard deviation here, which is the purple color, describes the area which have almost 68% of the cases, and outside of these two purple lines, I mean outside of the first standard deviation, there are less than 30% or 32% of the cases. This is okay. But if you look at the second city, which is totally different because it's not normally distributed, the standard deviation, the first standard deviation, does not only include 68, it probably includes almost 99%, and outside of these, the first standard deviation, almost like less than 1% of the cases. That's why in the case of non-normal distribution, the standard deviation may be misleading and may not be very useful. That's why in case of non-normal distribution, we rely on other metrics. I will show you very soon what are these other metrics. So before we go to the other metrics that are used in non-normal distribution cases, let's see what are the distribution cases. Actually, we have actual distribution. And actual distribution are mainly the things that we see in medicine or in biology, because most of the biological metrics are like actually distributed. They are not normally distributed, however, they are actually distributed. What does it mean, actual distribution in medicine? It means that you will always have an area clear area for central tendency where it's look like a pyramid or a bell shape. However, the two sides of this pyramid or these two sides of the bell shape are not identical. They are not symmetrical. For example, if you look at alkaline phosphatase, you will see that the values are a little bit skewed or stretched toward the upper limit. The same for the plasma glucose. The values are a little bit skewed to the upper side or the higher side, which means the right side. On the other hand, the blood hemoglobin is skewed or stretched to the left side, which is the lower limit. Okay, so as you can see in biology or in medicine, the values of populations or samples are not normally distributed, they are actually distributed. Again, what does it mean, actual distribution? It means that you have an area, clear area of central tendency where there is a bell shape or a pyramid, and then the two sides are not equal. On the other hand, and when we talk about mathematics or like perfect cases, we have normal distribution or Gaussian distribution or perfect distribution sometimes. And in normal distribution or perfect distribution, there is a clear area of central tendency where there is a bell shape or a pyramid. However, the two sides of this pyramid is identical. And unfortunately, we don't have something like this in medicine. And yeah, it's not so sad, but we don't have something like this in real life. However, most of our biological and medical parameters tend to be something like this or similar to this. Okay, so let's get back to descriptive statistics and remember the five numbers. What are the five numbers? The five numbers include minimum limit and maximum limit. This is the smallest possible value in the sample and the highest possible value in the sample. And then we have the median, which is the value that splits the sample into two equal halves. Then we have the lower quartile and the upper quartile. The lower quartile, which is the first 25%, the upper quartile, the 75th percent. Okay, so this is the five numbers that are used usually in descriptive statistics. The range, again, is the difference between the maximum limit minus the minimum limit. However, we have another concept which is called interquartile range, and this will be commonly used or combined with median sometimes, as you will learn soon. And this is the difference between the upper quartile and the lower quartile. So IQR or interquartile range is the difference between the upper quartile and the lower quartile, which is the 75th percent minus the 25th percent value. Here you have something that you have to do as a self-study, which describes when to use mean and standard deviation, because this is the common combination, mean and standard deviation, and when to use median and interquartile range. Usually, we use mean and standard deviation when the data are normally distributed, and we use median and interquartile range when the data are not normally distributed or when they are actually distributed or when they are skewed, okay, or when we have too much outliers that affect the mean and make it like too far from median. Okay, I will keep this slide for you for self-study, and now we will go to for inferential statistics. Inferential statistics, or sometimes we call it as analytical statistics, is very important because it helps us to make evidence-based conclusions based on the data we have in our hands. And usually we use this data from small samples, and we aim that by examining these small samples, we can make generalizations for the general population. So you will get a sample from your general population, and you try to generalize the results from this small sample on your general population. But be careful, because the generalization cannot be done straightforward. It has some techniques, and you will learn these techniques like hypothesis testing and estimation. If you look here, you can see that the general population, which is in blue color, has a mean of 49.64, which is, as you can see, the red line. However, the sample that was taken from this population, that is in orange color, has a mean of 48.15. Yes, there is some difference between 48 and 49.6. However, this difference is not always visible, and this is a challenge that we have in medicine and epidemiology, that once we have a sample, we cannot see the entire population because it's not practical, of course, to examine everyone in the population, and that's why you need to follow some techniques to estimate and see how much your sample is far or close to the general population or the true population metric. Okay, so Populations refer to the entire group, as you can see, the large population or the target population that we need to examine. It encompasses all items or all individuals that we need to examine supposedly, and the sample is just like a small subset of these general population that will definitely have some criteria or some characteristics that reflect the characteristics that are in the general population, and the closer or the more similar these sample to the general population, the better outcomes or the more reliable outcomes that we can get from it. So let's start with the first technique of inferential statistics, which is estimation. Estimation simply is the procedure or the practice of using data from a sample to infer characteristics about a broader population. So look at this graph. In this graph, we have a general population which is in blue color. Of course, we cannot examine all the individuals in this population. That's why we decided to take random samples from this population. For example, we have the yellow sample, which is sample number 1, sample 2, which is green, and sample 3, which is purple. And when you look at the mean of each of these samples, which is in different colors corresponding to the sample color, you can see that some means of these samples are very close. Like, for example, the sample mean, the sample 1 mean is 49, and the true population was 49.8, which is exactly similar. But in sample number 2, the mean is far. Sample number 3, the mean is also far to the other side. So it's not easy all the time to make sure which sample was the closest one to the general population mean. And remember that in real life or in epidemiological studies or even in clinical trials, you cannot see the general population. You cannot examine everyone, as we said. So you will keep relying on the samples, and you need to have some methods to tell you how much your sample is far or close to the general population or the true population metric. So the first metric we use is called the point estimation, and this is straightforward because it's just a single point, and this single point describes the mean of the sample that is supposedly reflecting the mean of the population. The second metric that should be used in combination with the point estimation is called the interval estimation, and this is important, as I said, because it describes the range or the interval in which the population parameter or the population mean should be located. So by 95%, you would say around my average or around my sample average, the true population effect should be here, or by 99% or by 90%. It depends on how much precision you need to have or you would like to have. So if you look in this second graph, you will see that the point estimate or the mean of the sample is in red color. However, it has a range of values that is in like blue, and this range, as I said, is called the 95% range or the 95% confidence, and this describes the range within which the true population value is supposedly located. Okay, so the point estimation and interval estimation are very important to tell us how much our sample is far or close to the general population. The smaller the interval estimation, I mean the shorter this blue line, the more precise our sample is. Okay, and then we have another technique which is hypothesis, and I would like you to pay attention to the next few slides because it will be really important not only for your exams but also for you to understand all the papers or all the medical literature that uses inferences. Okay, so what is hypothesis? Hypothesis, simply according to the dictionary, is a supposition or assumption that is arrived from observation or reflection that leads to refutable predictions. So this is a suggestion that can be either accepted or rejected. These are the two possibilities of any suggestion. Either you accept it or reject it. An alternative definition is that it's any conjecture that is cast in a form that will allow it to be tested and refuted. Also, according to Cambridge Dictionary, hypothesis is an idea or explanation for something that is based on known facts. So of course we need to make this suggestion based on previous information, and it has to be proven or rejected. So it has to be tested, and once we test it, we will be able to decide whether we should accept or reject this suggestion. Okay, so this is simply the hypothesis. According to the epidemiology glossary of the US CDC, hypothesis has two components. the null hypothesis and the alternative hypothesis. These two statements, which are the components of any hypothesis, are opposing to each other and they are equal to each other in terms of possibilities or probabilities. And once we do the research or once we collect the data that will tell us which one we should accept, we can decide whether to accept the null hypothesis and reject the alternative hypothesis, or we will reject the null hypothesis and on the other hand accept the alternative hypothesis. So what now the null and alternative hypothesis, or what are these two components? The null hypothesis is the probability or the first step in statistical significance, which means that there is no difference between people who are smoking and people who are not smoking in terms of cardiovascular disease, or there is no difference between the people who are treated and the people who are not treated in terms of clinical improvement. The drug has no clinical improvement or clinical effect. These are usually the old information. This is usually the common proposition or the prevalent knowledge. So all previous information or all previous knowledge or the probabilities that suggest that there is no difference between the individuals or between the patients or between the people who receive the medicine and who are not, these are all supposedly the probabilities that are called the null hypothesis. On the other hand, the opposing probabilities that are called alternative hypotheses, these are the hypotheses that should be adopted in case that the null hypothesis was wrong. So if the null hypothesis was wrong, we will definitely accept the alternative hypothesis because there is no other possibility, in fact. So the alternative hypotheses are usually the hypotheses that are adopted by the researchers. So if you have a new medicine or a new drug and you would like to say that it is effective, in this case, your idea that this drug is effective is in fact an alternative hypothesis because it challenges the old idea or the old information that this drug is not effective or there is no difference between the people who receive or do not receive this medicine. These are usually the new theories. I mean, again, the alternative hypotheses are the new theories or the researchers' ideas or the theories or sorry, the statements that assume there is a difference between smokers and non-smokers, assuming that this is a new idea or a new theory yet. There is association between smoking and lung cancer, for example. The medicine or the drug is effective. So all these probabilities, which are called alternative hypotheses, can be accepted once the null hypothesis is rejected. So simply speaking, as a researcher, your main aim is to find the data or evidence that will help you to reject the null hypothesis. And in case that you rejected the null hypothesis, you automatically promoted or accepted the alternative hypothesis, which is your idea. Okay, so you have to be careful. You should not be too much biased toward rejecting null hypothesis because null hypothesis can be in fact true, right? So let's see this exercise before we jump to the probabilities. In this exercise, I would like you to think about what is the null hypothesis and what was the alternative hypothesis. It is believed that a candy machine makes chocolate bars that are on average 5 grams. This is the average weight of these chocolate bars. A worker or someone or a scientist or a researcher, like any human, claims that the machine after maintenance no longer makes 5 grams. So 5-gram bars. So we have an idea that was prevalent, the common idea, which is on average 5 grams, and we have also a new idea that it's not 5 grams anymore. So the null hypothesis in this case will be that the average weight of the chocolate bars of this machine is 5 grams. However, the alternative hypothesis will be that the average weight of the chocolate bars from this machine is not 5 grams. Yet it can be more, it can be less, it doesn't matter, but it's not supposedly 5 or close to 5, okay? Because it has to be different in order to say that the worker had a correct idea or like right idea. Okay, so as you can see, the null and alternative hypotheses are mathematical opposites because if one of them is wrong, the other one will be definitely correct or right, and vice versa. So the possible outcomes of any hypothesis or any research testing or any hypothesis testing is that you can either reject the null hypothesis, and remember, once you reject the null hypothesis, you automatically promote and accept the alternative hypothesis, or maybe you're gonna fail to reject the null hypothesis, and if you failed to reject the null hypothesis, which means that you accepted the null hypothesis, you automatically rejected the alternative hypothesis. Okay, let's imagine that we had a sample of 50 chocolate parts from this machine after maintenance, and we weighted the chocolate parts, each of them, and we calculated the average value or the average weight, and now we will see what was the average value. So maybe the average value could be 5.12. If you see 5.12, you would say, this is almost 5, so I don't believe that the candy machine had changed after the maintenance, and that's why you will be more or less in favor of accepting the null hypothesis and rejecting the alternative hypothesis, or not believing the worker. If the size was 5.7, sorry, if the weight was 5.7, you would say in this case, I think it's probably not 5 anymore, because 5.7 is rounded or approximated to 6, not 5, and that's why you will tend to believe that it's not 5, and you will tend to believe the worker, and that's why you're going to reject the null hypothesis and accept the alternative hypothesis. But think about it, if it was 7.2, in this case you will blindly reject the null hypothesis and you're going to definitely accept the alternative hypothesis. That's why the farther you go from the null hypothesis value, the more sure you will be. But where is the question? Where is the line that we should use in order to decide? And this is exactly the statistical significance that we will see in the next few slides. But before we go to statistical significance, let's see another exercise here. In this exercise, you need also to write down what is the null hypothesis and what was the alternative hypothesis. Doctors believe that the average teen sleeps on an average no longer than 8 hours per day. So this is like the average sleeping duration for teens. A researcher believes that teens on average sleep longer. So doctors think that it cannot be more than 10 hours. However, the researcher believes that this is not true, because an average teen could sleep longer. So the null hypothesis in this case will be 10 or less, because this is the common idea or the common proposition among doctors. However, the new researcher or the new idea, which is the alternative hypothesis, mean that it will be more than 10 hours. So once you do the study and once you get the average duration of sleep for teens in your city or in your society, then you can see whether it's close to the null hypothesis or it's close to the alternative hypothesis, and based on this you can either accept or reject the null hypothesis. Okay, so let's see the errors that you can make based on these decisions. You can make what we call the type 1 error, and type 1 error is rejecting the null hypothesis when it is true. So the null hypothesis may be true, but once you decide to reject it, you are making a mistake. And usually you make this mistake because you want to believe that the drug is effective, or you want to promote the alternative hypothesis. But be careful, because the alternative hypothesis may be wrong and the null hypothesis would be correct. But if you insisted on rejecting the null hypothesis while it was true, you are making a mistake, and this mistake is called alpha or type 1 error. On the other hand, you may do the opposite thing, and you may accept the null hypothesis while it was false. So again, the null hypothesis might be false and the drug was effective. So if the drug is effective, it means that the alternative hypothesis is correct and the null hypothesis is false. But in case that you decided to ignore the idea and you decided to keep insisting on accepting the null hypothesis while it was false, you are making another error, which is called the beta error, and this is called the type 2 error. So let's look at this table. In this table, we think first of all on the null hypothesis. We try to focus mainly on null hypothesis, not alternative hypothesis, in fact. And null hypothesis can be either true or false. Okay, these are two possibilities. And the decision that you will make is either to accept or reject the null hypothesis. So you have null hypothesis, which could be true or false, and decisions that can be either to accept or reject the null hypothesis. If you accepted the null hypothesis while it was true, this is a correct decision, and this correct decision is called the confidence level, or C. and this is the probability, which is 1 minus alpha. However, if you rejected the null hypothesis while it was true, as we say, this is called type 1 error or probability alpha, and this is called as significance level. We will learn later about this terminology, I mean confidence and significance level. On the other hand, if you accepted the null hypothesis while it was false, you are making a mistake, because you should not accept something that is false. And this is called the type 2 error or beta error. However, if you rejected the null hypothesis that was false, in this case you are making a correct decision, and this correct decision is called the power of test or probability, which is 1 minus beta. Okay, the type 1 error sometimes is seen as false positive. Why it's false positive? Because you are rejecting something that is true. Okay, that's why it's seen as saying that this drug is effective while this drug is not effective. On the other hand, when you make a type 2 error or probability beta, this is false negative. Why it's false negative? Because you say that this drug is not effective, but in fact this drug was effective. Okay, so this is the type 2 error. Why it's false negative? Again, because you're accepting the null hypothesis. You are rejecting the fact that the drug is effective, however the drug is effective. So you give a false statement again. Okay, so let's see the confidence level, which is C. C, as we said earlier, is the probability of accepting the null hypothesis when it is true. So this is a correct decision, and we hope that we make it. We hope that we make this correct decision. And the type 1 error, which is alpha, this is the probability of rejecting the null hypothesis when it is true. So we can say it in other words, like the probability of accepting the alternative hypothesis when it's false. Okay, so when you look at C and alpha, you can see that C is equal to 1 minus alpha, and also alpha is equal to 1 minus C. And think about the null hypothesis as a true situation. So if the null hypothesis is true, this pretty much means that the drug that you try to prove its efficacy is not effective. So this is the reality. Okay, but before we do the study or before we do the clinical trial, we need to decide what should be our confidence level and what should be our alpha level or our type 1 error before we collect any data from the patients. Okay, and let's assume that whatever decision that we will make in the future or after collecting data from the patients should be 90% correct, which means that 90% in case of accepting the null hypothesis, that the null hypothesis should be true, and only by 10% error or wrong, which means that if you reject the null hypothesis when it's true, this shouldn't be more than 10%. You may choose that, okay, 90 is too much and I would like to have less or like more relaxed, and this would be 80. And in this case, if you have a confidence level of 80, the significance level or alpha should be 20. And maybe you would like to be more conservative and you would like to make a decision with higher confidence, and in this case if you increase the confidence to be 95%, I mean if you would like to increase the probability of making a correct decision by accepting the hypothesis when it is true, this should be 95%. In this case the alpha would be 5. Okay, so as you can see, once the C increases the alpha decreases and vice versa, because the total probability, which is H0 is true, is 1 or 100% at the end. Okay, so this is the relation between confidence level and type 1 error. And in medicine, just for your reference, the most common value we use in medical research is C as 95%, which means that the significance level in medical literature is usually 5%. Okay, so we say that by any possible mean, after we do the research or after we do the study, if we decided to accept the null hypothesis, it has to be true by 95%. And in case that we rejected the null hypothesis while it was true, this probability or this mistake shouldn't be more than 5%. So think about it. If you would like to reject something that is true, would you like to make it as 50%? I mean, to make this error by 50%? Of course not. You need to decrease it too much to as much as possible. That's why the null hypothesis has to be rejected only when it's true by a very small percentage, which is in this case 5%. But what if the null hypothesis was false? In this case, you need to reject it. and you need to make this decision by high level of certainty, and this is simply the power of test. So power of test is the probability of rejecting the null hypothesis when it is false. Also, you may make a mistake, and this mistake could be by accepting the null hypothesis which is false, and this is type 2 error. So type 2 error, or beta, is the probability of accepting the null hypothesis when it is false, or other hands or other terms, you can say it as the probability of rejecting the alternative hypothesis when the alternative hypothesis is true. So again, bar of test is 1 minus beta. Again, if you think about the null hypothesis as false, which means that the drug is effective, or the alternative hypothesis is correct, you have different scenarios. You can make power of test as 90%, and this makes the beta as 10%, or you can make it as 80% and beta as 20%, or make it as 95% and beta as 5%. Again, the standard value in medical literature is beta as 20, because as you will understand soon in the next comparison, that the probability of making beta error is less common than the probability of making alpha. That's why we shouldn't be very much worried about beta compared to alpha, because alpha is more common, because as a researcher you are biased toward believing your idea or believing your alternative hypothesis, which is the researcher hypothesis, more than doing the opposite, or rejecting your own idea and promoting the null hypothesis. This is not very common, I mean, according to our human nature. That's why we need to be very careful from the type 1 error or alpha, and make it as less possible as possible, and in order to do this you need to squeeze the probability alpha and make it as 5%. However, in probability beta there is less likelihood to make it, and that's why you can relax it until 20. And there is also one more reason why beta can be relaxed, or should be relaxed a little bit more than 5%. It should be, as I said, usually 20, and this is what you will see soon. So in this table, you can see a comparison between type 1 error and type 2 error. In type 1 error, the definition is, as you remember, is to reject the null hypothesis when it is true. Type 2 error is, on the other hand, accepting the null hypothesis when it is false. So as you can see, both of them are mistakes. One of them is rejecting something which is true, and the other one is accepting something that is false. Again, as I said earlier, there is more likelihood for type 1 error to occur because the researchers by default aim to accept the alternative hypothesis. They try to prove that their medicines are correct. That's why they are more biased to reject the null hypothesis. And again, there is a risk that they could reject the null hypothesis while it was true. On the other hand, in type 2 error, there is less likely to happen, and there is also less likely to focus on its measurement. That's why we don't really set the threshold for beta. We rather focus on the bar of test, which is 1 minus beta. And the 1 minus beta need to be as high as possible, as much high as possible, because these describe something that we need to do, I mean, certainty and correct decision, but you have to be careful, because once you increase the beta, you will have to increase the sample size. However, in the type 1 error, either in significance or in confidence level, like these two concepts for the type 1 error, the sample size does not get affected. That's why if you have 5% of alpha, or 10% of alpha, or even 1% of alpha, which is type 1 error, the sample size could remain the same. However, in the 1 minus beta, which is power of test, if you have 80%, then the sample size could be 300. But if you have 90%, the sample size could be 10,000. Okay, so you have to be careful. You have to be careful with the 1 minus beta, which is power of test, because it will increase the amount of people need to be recruited for the trial, and this definitely is associated with increased costs. The type 1 error may lead to false claims, which is, as we called earlier, the false positive, because it can say that the drug is effective while it's not effective. However, the type 2 error makes the opposite, which is false negative, because it may miss a significant effect or relationship. So the drug could be effective, however, the results or the researcher could say that it's not effective. So this is also a loss. This is also a mistake that we don't want to make, because it may make us lose like interesting results or effective medicine, and not seeing their true effect. Okay, so as you remember, all these were assumptions for the values that we need to set before we do the study. But once we finalize the research and we do the study and we do our analysis, our statistical analysis, we will get to a value which is called the p-value or significance value. And this is the probability of observing a test statistic as extreme or more extreme than the one calculated given the null hypothesis was true. Okay, so what does it mean? It means that the significance level, which was alpha, that we agreed about as 5% or 0.05 from the beginning, need to be compared to the p-value. So alpha will be the threshold that is used to compare the p-value. If the p-value is less than this alpha, it means that we can fairly reject the null hypothesis because this does not make us making a mistake. Okay, you have stronger evidence now against the null hypothesis. However, if the p-value or the value that we get from the actual data or from actual study is greater than the significance level that we assumed earlier or assumed before the study, in this case we have to be careful. You cannot reject the null hypothesis, because if you rejected the null hypothesis in this case, you would be definitely making an error, which is type 1 error, or you are making a mistake. So again, let's see this in this graph. So this is the probability of the null hypothesis when it is true. So if you set the limit as 5% for alpha, and after the study you get a p-value from your research or from your sample as 0.02, then your probability is lying here, which is the 5%, and this is the safe area, by the way. So in this case you have stronger evidence to reject the null hypothesis, because the null hypothesis in this case may not be true, or actually it's less likely to be true. However, if the p-value lied here in as 0.07, this is the result we get from our study, in this case you have to be careful because you already crossed the line, you crossed the border, which is the black border. Earlier you say that the threshold, which is the alpha, should be 5%, and now you have it as 7% from the significance value. And that's why you need to be careful. You cannot reject the null hypothesis in this case. In a nutshell, if you have low p-value, you should reject the null hypothesis. If you have high p-value, and high here means higher than the significance level or the assumed value from the beginning, in this case, you should not reject the null hypothesis. You should, in fact, accept the null hypothesis and reject the alternative hypothesis. Okay, so now let's see how we get the p-value. I know that this table is a little bit messy, but it has 4 columns. I want you to read the first column and compare it to the second one. So let's see the first situation. In the first situation, we are trying to study the association between 2 qualitative variables. So the variables that are involved here are both of them qualitative, like for example, gender and smoking. Smoking can be smoker or non-smoker. Gender can be male or female. So both variables are qualitative, and that's why the test that we're gonna use here is called the chi-square test or the Fisher exact test. We're gonna use chi-square test once we have great sample or good number of individuals. But if we have a small sample, like less than 5 individuals, usually in this case we're gonna use the Fisher exact test. So for great samples or for normal samples we use chi-squared, and for small samples or for small number of individuals we use the Fisher's exact test. And in another situation, you would like to see the single quantitative variable, like you have only one quantitative variable, and for this you're going to use the student t-test or the one sample test. And you actually do this situation, or you do this analysis, because you want to compare the sample mean, the mean of your sample, to a general population mean. So you have a general population values that you learned probably from other research or from other reference, and you would like to compare how much your mean of the sample, or sorry, the mean of your sample is close or far from the true population. And the statistics that is used to get the p-value in this case is called the student t-test or the one sample z-test. And the one sample z-test is actually used when the sample size is large or the population variance is known. Okay. Sometimes we have 2 variables. One of them is quantitative and another one is qualitative. If both variables coming from 2 unrelated groups, like male and female, these are 2 unrelated groups, in this case you're going to use the independent t-test. If both of them coming from the same group, like this can be a group that is tested before an intervention and after intervention, like before treatment, and the same patients have been retested after the treatment, then in this case you're going to use the paired t-test. And if you have to compare between more than two groups, like 3 groups or 4 groups, in terms of some quantitative variable like blood glucose level or blood pressure, in this case you're going to use the ANOVA test or the analysis of variance. You can see that there was also Mann-Whitney test, Wilkinson signed rank, and Cross-Calvalis test, and all these tests are the non-parametric tests from the independent or the Bayer test or the ANOVA test. What does it mean, non-parametric? It means that those are used when the distribution of the numerical variable or the quantitative variable is not normal. So if you see in your data that the numerical variable, which is in this case the quantitative variable, is not normally distributed, then you're going to use the Mann-Whitney or Wilkinson signed rank or Cross-Calvalis. Finally, we have sometimes two quantitative variables, and for quantitative variables, if you have two of them, you can see the association or the relationship between them using correlation tests. We have Pearson correlation and Spearman correlation. Pearson correlation is used when the quantitative variables are normally distributed over each other, or if they are not normally distributed, then we're going to use Spearman's rank correlation. Okay, so let's see the examples we have. The first example is when you try to see if there is association between sex and smoking, I mean being male or female, and the status of smoker or non-smoker. So this table describes these numbers. So you have 1,000 females and 1,000 males. Among the 1,000 females, 100 were smokers, and among the 1,000 males, there were 400 smokers. So based on this distribution or these numbers, you can see two categorical variables. Sex is a categorical variable, it's either male or female, and also smoking is a categorical variable, it's either a smoker or non-smoker. So in this case, we will definitely use a chi-square test. And the chi-square test, if we calculate it, it will lead to a p-value which is less than 0.0001, which is extremely small, and that's why we can fairly say that the smoking habit is significantly more common with males or in males, or in other terms you can say that male gender or male sex is significantly associated with an increased risk of smoking compared to female gender or female sex. There is some online tools to calculate the chi-square test if you have raw data, and this is one of them, and I will just keep it here if you would like to use it later on. And this is for the samples that I used. If you'd like to see the raw data that I used here, I will have a lot of examples for you in the classroom, so don't worry. I mean, you will have training on this in the classroom, but for now you just need to keep in mind that whenever you have two categorical variables or two qualitative variables, either categorical or ordinal, you should use a chi-square test or Fisher exact test if the sample is too small. Actually here the sample was large, so we didn't need to use a Fisher exact test. We used the chi-square test because the sample was large. Okay, this is the first scenario. The second scenario here, if we would like to focus on smokers, and we would like to see if there is some difference between smoking frequency between smoking females and smoking males. And that's why we have two variables. One of them is categorical, again it's 6, and the other one is quantitative or numerical, and this is the smoking frequency. But remember that the qualitative variable here, which is 6, has two independent groups. These are two separate groups. Okay, so if you look at this table, you have 50 females and 50 males. Both of them are smokers. The smoking frequency among females was on average 10 cigarettes per day. However, for males it was 15, and the total was 100 individuals, as you can see, and the average smoking frequency was 12.4. So as you can see, before we do any statistic, yeah, males tend to smoke more than females. I mean, among smoking males and smoking females. And in this case, we have two independent groups, two separate groups for the qualitative variable. And for the quantitative variable, we have a continuous variable or number. That's why we're going to use the independent t-test. And again, the independent t-test is used because the qualitative variable has two independent groups or groups that are like distinct from each other. They are not the same. And the other variable is the quantitative variable, which is the number of cigarettes. And once we did the analysis for these like groups, we had found that the p-value was also significant. It was less than 0.0001, and this is a free tool that you can use to get this p-value and in the classroom again we will train on this. In another scenario, you could have counseling, and in counseling you test the same groups. This is the same sample, and you test them before counseling and after counseling. So you would like to see the smoking frequency before counseling and after counseling. You want to see before counseling how many cigarettes you were smoking, and after counseling how many cigarettes you were smoking. And this is sometimes called the pre-test score and the post-test score. So in this table, you can see the before counseling and after counseling. The cases is almost 40 because this is the same individuals. They have been tested twice. They have been tested before the intervention and after the intervention. As you can see, before interventions, they had on average 21, and after interventions, they had on average 17, which is great. Like there is progress in terms of reduction. And in this case, we're going to use also a t-test, but this t-test is not called independent t-test, it's a paired t-test, and sometimes we call it as the dependent t-test or the dependent two sample t-test, because the one sample t-test, because this is the same sample that has been tested twice. And again, when we did the analysis for this, we found out that the p-value was significant. It was less than 0.00001, and this is a free tool that you can use to get these values. I will, as I said in the classroom, share the raw data. One more example here, which compared two variables. One of them is qualitative and the other one is quantitative. The qualitative variable here is the academic level, which is ordinal qualitative variable. You can be either in first year of college, second year, third year, fourth year, or fifth year, right? On the other hand, the anxiety score is a score that is measured on a scale from 0 to 21, and the higher score, the more anxiety level that you could have. That's why these are two variables. One of them is ordinal, which is described using words like the academic level, and the other one is measured using numbers. And in case that you look at this table, you can see that in the first year, we tested 20 students, like randomly from the first year of college, and the anxiety score was 9. The second year, the average anxiety score was 12.8. The third year was 13.2, the same for fourth year, and the fifth year was 16.4. And the average for all these 100 students that we collected from all the 5 classes was 12.9. Okay, so in this case, you have more than 2 groups for the qualitative variable, which is 5 groups in fact, and the quantitative variable is also number. That's why we're going to use the ANOVA test or the analysis of variance. Okay, and when we did the analysis for this sample, it was less than 0.00001, and this is a tool that you can use to get this p-value. Finally, we have an example of 2 quantitative variables. One of them is the BMI, which is the body mass index, and this, as you remember, the ratio between weight and height in meters and in kilograms according to the metric system. And the other quantitative variable is the blood glucose. So we assume that the higher BMI should be associated with higher blood glucose or higher risk of diabetes mellitus. And in this list of individuals, we have 10 humans who are obese. The first case had 31 BMI and 150 fasting plasma glucose. The second one has 31 also and fasting plasma glucose of 170. The third one 36 BMI and 180 fasting plasma glucose, and you can read the list of the variables, the values in this list. So if you have 2 quantitative variables, you should use a correlation test, and it can be either Pearson or Spearman correlation. I will not really push you to tell me the difference between Pearson or Spearman, because you will not be able to do it here. I mean, to measure it, but you need to keep in mind that Pearson is used for normal data, Spearman is used for non-normal data. And for this, it was normal, that's why we used Pearson. And when we did the correlation analysis, we found out that the correlation coefficient was 0.8 and the p-value was less than 0.05, which means that the association or the correlation, this is the correct word here, it should be said as correlation, the correlation between body mass index and blood glucose level was significant. So it was significant correlation, and it was positive and strong correlation, because as you can see in this line, the distribution of the points is in like positive way or positive trend. This is also the tool that you can use from the same website. It's a free tool, and we will try to use it as much as possible in the classroom to make you see how we calculate the p-values and interpret them. Okay, so there is a part for your self-study that is from your textbook, and it's about abnormality. We can define abnormality using different philosophies or different methodologies, and this is what you need to read from your textbook. Now let's see prognosis and survival. So prognosis is a concept that we use in medicine to understand what will happen for the patients that are suffering from a disease at the moment. So we use cohort studies also for prognosis, but these cohort studies that we use for prognosis are different from the cohort studies that we talked about in the previous seminar, which are cohort studies of risk. Because cohort studies of risk or prospective cohort studies are recruiting two groups of individuals that are healthy. But here in prognosis, we recruit two groups of individuals that are sick with the disease, but maybe they have different stages of the disease. Maybe we compare between stage 3 and stage 2 of cancer. Maybe we are comparing between males and females. We are comparing between old people and young people who are sick. So the patients or the people who join prognostic studies are usually patients, and all of them have to be patients, in fact, but one of them is different from another one in some or few or one even characteristic. So we need to keep in mind that the moment when we recruit the patients is ideally the first moment when the disease is diagnosed. So when the disease is diagnosed, we should recruit the patients as much as possible, and this is called the inception cohort. Otherwise, whenever the patients start to be recruited in the study, the first moment they are recruited in the cohort study, this is called the zero time. So the zero time assumes that this is the time when the disease started, and it's not always the case. That's why we try to do our best to make the zero time is the time of onset, or the time when the disease actually started, and that's why we call it assumably, or like hopefully, the inception cohort. You have to be careful because in some diseases, especially in cancer, we have a very complicating phenomenon in prognostic studies which is called stage migration, and I will explain in the next slide what is stage migration, but just here you can see some common rates that we use to describe prognosis, like the 5-year survival rate, and this describes the percentage of patients surviving 5 years from the moment when they are diagnosed or when the disease started, supposedly. We have the response, remission, or recurrence, and all this is part of your self-study. I mean, this table and the related explanations from the textbook. Okay, so let's focus on stage migration in cancer studies or cancer prognostic studies and how it happens. So stage migration, in fact, is a phenomenon that has other terminology, which is Will Rogers phenomenon, and it's an issue that happens in cancer studies specifically because cancer has very rapid and very progressive area of research. So like every now and then we have new techniques and new diagnostic techniques specifically to diagnose for cancer. That's why with every new technique or every new diagnostic technique of cancer, the definition of the cases can also change. I mean, the one who is now considered as to be stage 2 cancer may be stage 3 later when we have new diagnostic method. The one who is classified now as stage 1, maybe after the new method is applied or like used, he will be or she will be classified as as a stage 2. The patient does not necessarily have worse outcomes or worsen outcomes, like he may have the same condition or the same symptoms and signs, but our definition or our parameters had only changed, and this change will lead to some interesting outcomes that you will see here. So in this graph, you can see that there are blue and yellow colors. The blue color represents the cases of cancer before the migration or before the new technique or the new diagnostic method was used, and the yellow one represents after the new diagnostic method is used, which is called the after migration. As you can see, in stage 1 and stage 4, there was no difference. After the new or before the new method, there was no difference. The same cases were diagnosed, the same patients were diagnosed in stage 1 and stage 2. However, in stage 2 and stage 3, the differences can be seen because in stage 2, before migration, we have more cases. However, these number of cases, like this 10% of the cases, moved from stage 2 to become in stage 3 after we use a new diagnostic method. And you will be surprised that those 10% who moved from stage 2 and stage 3, they will make the outcomes of both groups better. And that's why the prognosis of a stage 2 and a stage 3 will significantly improve. However, there is nothing happened, like the cases that are in stage 2 are still receiving the same medicines, and also the patients in stage 3 that are still receiving the same medicines. However, these improved outcomes or these improved prognosis happened because of pure mathematics or pure statistical differences. So let's see in this graph, because this graph will make you understand it better. So in the first graph, I mean the graph on the right, on the left side, you can see that stage 2, which is blue, and stage 3, which is yellow, are overlapping. So the most extreme cases, or the cases that have the highest risk in stage 2, are overlapping with the most mild cases in stage 3. And once we change these, and once we remove the most extreme cases from stage 2 and put them in stage 3, then the mean or the average outcome of each group will be lower, because you have removed the worst cases from stage 2, and that's why the mean of the stage 2 will decrease, and you put these cases to stage 3, and you have to keep in mind that those cases that have moved from stage 2 and stage 3 are less mild or milder than the average of stage 3. That's why they will decrease also the average of stage 3. So mean of stage 2 and mean of stage 3 will decrease, because you have moved the worst cases from stage 2 to put them in stage 3. They are worse than stage 2 average. That's why the stage 2 mean will decrease, and they are better than a stage 3 average. That's why also the stage 3 average will decrease. Okay, so this was the phenomenon of Will Rogers, or stage migration in cancer. Now let's see survival analysis. And when you interpret prognosis, you need to see how much the patients that are treated today from cancer or other disease will able to survive or live for the next few years. And that's why you need to look at an event or an outcome that will either happen or not happen. Either they will die or not die. Either they will have complication or not have complication. Either they will survive or not. So all these events that will be used as an outcome measure for survival is important to be dichotomous, or it's important to be binary, because they will either happen or not happen. And once you have decided this outcome that will not re-happen, like it has to happen only once in life, you can draw these graphs. So in the graph number A, you can see the dissecting aneurysm and how it leads to mortality within like the first 5 years. Unfortunately, the vast majority of cases die in the first year. That's why the survival probability within the first year is almost like 21 or 22%. In the second year, it's less than 20%. It's almost 15%. In third year, it's less than 15%, and it somehow stops at 10% by the fifth year. But you have to remember that most of the cases died in the first year. But if you look at lung cancer, the situation is a little bit different, because only 30% of the cases die in the first year. But unfortunately, by the second year, almost 60% of the cases die. So most cases die in the first 2 years, but they don't die all in 1 year. They die approximately in the 2 years, like equally, like the first year 30 and the second year also other 30. And then, as you can see, the number of number of survival also declines. The amyotrophic lateral sclerosis is probably the best out of all these diseases, because the less number of people die in the first year, then less number also die in the second year, third year, fourth year, but then once you reach the fifth year, the survival is almost 10%. So among these three diseases, after 5 years, the number of people who survive is almost the same, it's 10%. But the question is that, are these three diseases equal or similar in risk of mortality for like the patients who get them? Of course not, because many people can survive during the first year from amyotrophic sclerosis or from lung cancer. However, they cannot do the same for dissecting aneurysm, okay, because dissecting aneurysm has the worst survival in this case. Okay, so these graphs that you see here, I mean, all these four graphs are called Kaplan-Meier graphs, or Kaplan-Meier analysis, or survival analysis graphs. And if you have many patients in the graph, then the graph will look like as a smooth line. But if you have less patients, you will see it as a ladder or sharp line, because one case or few cases may make huge step. That's why it will not be smoothened. But if you have many patients or 1,000 patients, as you can see on the left-right graph, in this case, the line will be flattened and it will be smoothed. So the more cases or the more patients in the survival or in the prognostic study, the smoother the curve could be. And sometimes this curve or this Kaplan-Meier curve is called the time to event analysis. Okay, so let's try to read this survival curve. In this survival curve, by the third year of the study, we had 8 cases remained. I mean, 8 cases at risk. They didn't get the disease yet, or they didn't die yet. And within the third year, 3 left the study. They didn't want to continue. And that's why by the end of the third year, we had only 5 cases left at risk. I mean, those are still could die or could stay alive, and only one of them died. So that's why in this case, the survival rate is 4 cases out of 5, and it's 80%. That's why we lost only 20% out of the level here. Then by the end of the fourth year, we had 4 cases, 2 of them censored, which means that 2 of them left the study. We cannot know what happened to them. Maybe they died, maybe not. So what remained at the end of the fourth year is 2 cases that were remained at risk, and only one of them died and the other one remained alive. That's why the probability of survival here will decline by 50%, and that's why by the last year of the study we had less than, I think, 8% or less than 8% of overall survival. Okay, even though it was only one human. So in general, when you look at survival curves or Kaplan-Meier curves, the left side usually represent the years, I mean the early years of the study, where most of the cases were followed up, nobody left yet, not only because of they die, but because they don't want to continue mainly, or they don't want to continue cooperation, and that's why we don't have much censoring. But toward the right side, or the more you go with time, more people get bored or they don't want to continue in the study. That's why censoring is larger, and that's why certainty of the probability of survival toward the last few years in the prognostic study is lower. That's why we cannot be very sure what will happen in the last few years or the last 2 or 3 years, because things could change completely. Okay, so this is the survival curves. Survival curves also can be used to compare between different prognostic factors. Like in this graph, we can see like 3 prognostic factors, and the relationship between the different prognostic factors is called the hazard ratio. And the hazard ratio is very similar to what we already studied earlier, which was the risk ratio or relative risk. This is also part of your self-study, that's why you need to read it. Now let's move to another part, which is related to diagnosis that we talked about in the second seminar. Not all clinical manifestations or patient outcomes are physically measurable. If you think about blood pressure or body temperature or blood glucose level, these are all physical measures. That's why we can easily measure them, and we can get sensitivity or specificity or other accuracy values to decide which test we're going to use to measure them. But there are also other problems that humans or patients suffer from, but we cannot measure them physically. For example, mental health conditions like anxiety or depression or other mental disorders. Also subjective symptoms like pain or discomfort. All these are reported by the patients, and we have no physical methods to measure them. That's why we need to think about what can be done in order to examine them. And this is actually the instruments that are used for the psychological diagnosis, like for example questionnaires or structured interviews. So if you would like to say that someone suffers from depression, you need to give them the patient health questionnaire, which is 9 items, and they need to answer each of these 9 items using a scale from 1 to 4, and you're going to collect the response from the patients or from the suspected patients or whatever group that you are dealing with, and analyze it and see whom of them or how many of them are suffering from like severe depression or mild depression or moderate depression or extreme depression, or sorry, extremely severe depression. So these are all methods that we use, which are questionnaires or interviews, but these questionnaires or interviews need to be accurate and need to be reproducible, which means that we need to test them before using them. And that's why the concept of validity and reliability are crucial in clinical psychiatry and also for clinical medicine, because even if you're not like doing psychiatry in your future work, you still need to ask your patients about pain or discomfort if you are, for example, in either internal or surgical specialty, because you need to assess the outcomes. You need to see if there is improvement or not. And that's why the measures or the interviews or the questionnaires that are used for these diagnoses need to be, again, as valid or reliable. So what is validity and what is reliability? Validity is simply accuracy. You need to see the results that you are getting from your patient as much accurate as possible, as much descriptive for the reality as possible. And this is the validity. So validity is the degree to which the data measure what they are intended to measure, or the degree to which the results of a measurement correspond to the true state of the phenomenon being measured. Another way, or other word, it's called accuracy. We use this validation concept mainly for non-physical measures. And validity has three types. The first type of validity is called content validity, and this describes the extent to which a particular method or a particular questionnaire describes all the potential dimensions of the problem that is supposed to measure. For example, if you think about a scale that should measure pain, it should have questions about aching, throbbing, pressure, burning, or stinging, because all these dimensions describe the pains that patients or humans feel. However, itching, nausea, tingling, these are not pain. That's why we should not include them in the questionnaire or the survey that we use to understand about pain. This is content validity. So the more dimensions, and if the questionnaire can cover all dimensions of the phenomenon or the problem that we examine for, then we can say that this is a measurement, or this is as a questionnaire or an instrument that has high content validity. Then the other concept or the other quality of validity is called criterion validity. And imagine criterion validity as a ruler or as a scale. So it means that if you have a low score on the depression scale, in this case, the patient should have or should show the least mild, or sorry, the least aggressive or the mildest symptoms of depression. And if the patient had get like the largest possible or the highest possible score of depression, in this case, this patient need to have, for example, suicidal ideation or very like aggressive clinical symptoms of depression. Okay, so if there's correlation between the score of the measurement or the questionnaire and the severity of the clinical or the observable outcomes or the clinical symptoms, in this case, we can say that this instrument has good criterion validity. Then constructive validity is easily established if you have prior methods. So if you have developed a new method for diagnosing of depression, and your method, let's say that it's like a new one that you like made by your own, and it gives results that are similar to the results and are also in the same direction of the results from previously validated measures like from Harvard or from other like well-known institutions. In this case, you can say that your measure is in consistency or is in agreement with previous measures. That's why it has good construct validity. So these are the three concepts of validity that describe how much the instrument, that is a questionnaire or an interview, is valid or is accurate. Okay, so now let's go to reliability. Reliability is, on the other hand, does not really pay attention to how much you are measuring the reality or the truth, but by how much the results that you are getting are similar to each other. So let's imagine that you are repeating the experiment or the measurements like several times during the day. It's supposed to give you the same result if you are testing the same patient that have the same conditions. It cannot give you different result each time, because in this case, this will be unpredictable, and that's why the usability of the test or the questionnaire will be low. Okay, so reliability is simply about reproducibility or repeating the results once we have the same conditions. Okay, so it's precision or reproducibility. These are the other terminology. And reliability also has three main types. First is called test-retest reliability, and this pretty much means that the result that you need to get should be similar over the time. So if you test the patient today and after a few days you tested the same patient and assume that the patient did not have any clinical difference or any clinical improvement or any difference in their clinical outcomes, then it is important to see the same results. Okay, so if you can see from this example, a depression inventory like the big depression inventory should yield consistent scores when administered to the same patient and at different times. So if the same patient has the same clinical status, he should give the same result regardless on when they are tested. So every time or like over time, the result should be similar or should be the same. This is the first concept. So we do retesting for the patients over time in order to see if the results will change or not, assuming that the same clinical condition will be in the patient or remain in the patient. Then another concept is called inter-rater reliability, and assume that we have one patient or few number of patients and we tested them using a group of doctors. So if all these doctors have the same clinical experience and the same skills, we expect that all of them should get the same results from the interview of the patient, because this is the same human, this is the same patient that is that is examined by like supposedly equivalent physicians or physicians that have the same experience, and that's why the results of each patient, of each doctor for this patient should be the same. And if it's different, then in this case the method will have low inter-rater reliability. Inter-rater reliability means that if you are testing a group of patients by the same doctor before and after, or like in two different times, the difference between the same patients for like before and after, or like during over periods of time, should be very small or should be not different at all. Okay, so test reliability focuses on the similarity over time. Inter-rater reliability focuses on the similarity between different doctors. However, inter-rater reliability, which is a little bit similar to test retest, focuses on the similarity between the results of the same doctor or the same physician. So if the doctor did the examination twice during the day, in the morning and in the afternoon, and it's the same group of patients, the same group of patients should have results in the morning and the afternoon, because there shouldn't be any difference that happened. Okay, so this is the three concepts that describe reliability. If you'd like to see the relationship between validity and reliability, you can look at this graph. In this graph, we have white line that describes the true phenomenon or the true disease or the true value. In the graph number A, you can see a test that has high validity and also high reliability. But why it's high validity and high reliability? High validity because the mean of the scores of the sample is corresponding to the white line, so it's accurate. And it has also high reliability because the range of the values is very small, so it means that the test gives the same result every time it's used, or very like similar results. That's why it's high reliability. However, if you look at the graph number D, which is the last one on the right side, I mean the right bottom side, this is low validity and also low reliability. Why it's a low validity? Because the mean score is very far from the truth, which is the white line. Okay, and also it's a low reliability because the values are distributed over a huge range. So every time the test is used, it can give you a totally unpredictable result. Okay, so here we have low validity and also low reliability. In the case of the figure B, we can see high reliability and low validity. Why it's low validity? Because the mean score is very far from white line. However, the range of scores are very close, which means that it has high reliability. I mean, the results are not unpredictable. They are predictable every time we test, but unfortunately, they do not describe the truth. On the other hand, in the figure C, we can see high validity, but low reliability. Why high validity? Because the average score is corresponding to the true value. However, it's low reliability because the results are scattered over a huge range and they are extremely unpredictable. Okay, so these are the four possibilities and the four interactions between validity and reliability. Now let's see what is error and what is bias. Random errors are unpredictable. They like fluctuate around the true value. They have no intention, or we have no intention to produce them, and they happen because researchers are humans and mistake is like normal or natural in like our nature as humans. So it's normal. It's no problem with it. But we need to keep in mind that they can happen, and that's why we need to control for them. On the other hand, systematic errors, or what we call as bias, they are consistent. They will keep happening every time you repeat the experiment. And unfortunately, they will either increase or decrease the association or the p-value or other metrics that you are evaluating. So in this comparison, you can see what is a random error and what is a systematic error, or what we call the bias. So the random error can affect the precision, but it will not affect the validity. So it will affect the reliability, but it will not affect the accuracy. However, the bias will affect both of them. Okay, the bias will affect both the reliability and validity. If you would like to remove or control the random error, you will either increase the sample size or you will do some statistical adjustments like standardization or stratification. This is what we learned in the third week about the methods that we use to control for confounding, for example. Okay, so the statistical methods or the statistical techniques that are used to control for confounding factors can be used also to control for random errors. However, for systematic bias, the best and probably the only effective method to control them is to do modifications during the study design, like randomization or blinding or matching or restriction. These are all uh, different like techniques that can remove or control the systematic error or biases. The problem with random error is that it leads to widening of the confidence interval. So the confidence interval will increase, and this is not really good because you need to have a small confidence interval to make sure that the true value will be within this small confidence interval. But if the confidence interval is large, it means that you have less certainty about where the population true effect is located. However, in the systematic error, the confidence interval itself will be totally shifted. It will be totally moved from or migrated from its like true location. Examples for random error can be laboratory error or recall error, and this is part of your self-study from the textbook. And for systematic error or bias, we have selection bias and information bias. As a quick summary for the types of bias, I can show you here that this is a timeline of a cohort study. At the beginning, you can do sampling bias, and this can happen when the patients in one arm of the study are different systematically from the patients in the other arm or in the other group. You can do migration bias, or migration bias you are not basically doing. This happens to you because the people who are supposedly followed during the study may move or may leave the study, but unfortunately, if they moved from one group over on the expenses of the other one, or if one group is severely affected compared to the other one, this is called migration bias, and you need to do some techniques to control for it, and this is are all statistical techniques, and it's called sensitivity analysis or best case worst case analysis. You need to read this part from your textbook. Finally, at the end of the study, you can do unfortunately some measurement bias, and these are related to the methods that you use from or in your analysis or in your measurements, because you may send all the samples from one group to certain lab and the other group to another lab, and there could be differences in the labs, not in the samples. That's why there will be difference in the samples results, but you will not be sure if this difference is because of the lab or because of the samples themselves. Okay, so thank you so much, and I hope that this was not very difficult for you, and see you this week in the classroom.